Okay, so let's start our discussion for the second quarter, which is all about the atomic structure and the quantum mechanical model. But before that, let me first discuss what you are going to do for this week. First activity is electron configurations. Materials you needed in this activity is a pencil and periodic table of elements. Procedure: write the electron configurations for the elements in the third period of the periodic table. 2. Compare the electron configurations for the first 10 elements. See Table 3 for comparison. So in this table, you will see chemical symbols: H for hydrogen, He for helium, Li for lithium, Be for beryllium, B for boron, C for carbon and nitrogen, O oxygen, F fluorine, and Ne neon. From the second column to the sixth column, you will see the orbitals, and for the last column, the electron configurations. After you write the electron configuration for the elements in the third period, you will answer the 3 guide questions. First, do you see patterns in the distributions of their electrons? Number 2, what are these patterns you observe? And 3, what do you think are some rules apply in filling up the orbitals for the element from atomic number 1 to 18? Next activity is the quantum theory and the atom. You will answer the 5 questions. 1. In Bohr's theory of the atom, energy levels of an atom are said to be quantized. What is meant by the term quantum energy? Second question, both the Bohr model and quantum mechanical model of the atom involve quantized energy levels for electrons. How are the models different in their description of the electron location? Number 3, define Heisenberg's uncertainty principle. 4, define the term atomic orbital. And last, 5th question, sketch the shapes of the s, p, and d orbitals. Okay, so let's start the discussion. Atom. Atom is the building blocks of matter made up of protons and neutrons inside a central nucleus surrounded by orbiting electrons. Okay, so this model that you can see on the right side of the screen is the planetary model by Ernest Rutherford. This model of the atom beside is the one of most people learn in chemistry classes at school, called the planetary model, which is the model of atom that appears like a planetary system, with the nucleus acting as the sun and the electrons acting as the planets. Okay, so what is the quantum mechanical model, or what is the origin? The discovery that began quantum mechanics as a field of study is when physicists Albert Einstein and Max Planck proved that light and matter can behave both as particles and waves. This began the era of quantum mechanics, which is basically the basics of the very tiny. In other words, when we are saying the quantum or quantized, it deals with the smallest unit of a matter. If particles like electrons can behave as waves, it means that they don't have exact position the way we would imagine for a traditional particle. Quantum mechanics tell us that you can precisely know both the position and velocity of an electron at the same time. The quantum mechanical model. 2 models of atomic structures that are still in use today is the Bohr model and the quantum mechanical model. The quantum mechanical model is based on mathematics. Although it is more difficult to understand than the Bohr model, it can be used to explain observations made on complex atoms. To understand what is quantum mechanical model is all about, let's first look at the definition of the word quantum or quanta. In physics, a quantum or quanta in plural form is the minimum amount of any physical entity involved in an interaction. Behind this, one finds the fundamental notion that a physical property may be quantized, referred to as a hypothesis of quantization. This means that the magnitude can take only certain discrete values or the smallest number. Why is energy quantized, or why it is need to be quantized? After Max Planck determined that energy is released and absorbed by atoms in certain field amounts known as quanta, Albert Einstein took his work a step further, determining that radiant energy is also quantized. He called the discrete energy packets called photons. Einstein's theory was that electromagnetic radiation, or the light for example, has a characteristics of both a wave and a stream of particles. So this is the dual nature of light. In this image, there is a light source which is the bulb, and shows the two nature of light, in which light behaves as a particle and light as a wave. In the light source, when you put a barrier, light travels as a particles is blocks, then again scatters, while in waves that behaves like a wave, when you put a barrier, the waves bends into a shadow. Okay, next, the Bohr model. In 1913, Niels Bohr used what had recently been discovered about energy to propose his planetary model of the atom. In Bohr model, the neutrons and protons are contained in a small dense nucleus, which the electrons orbit in a defined spherical orbit. He referred to these orbits as shells or energy levels, and designate each by an integer 1, 2, 3, and etc. An electron occupying the first energy level was thought to be closer to the nucleus, since it is the nearest to the nucleus and have a lower energy than one that was in numerically higher energy level. So, if an electron is assigned on the first energy level or energy level 1, this means it has lower energy than the electrons assigned energy level or the energy level 2. Bohr theorized that energy in the forms of photons must be absorbed in order for an electron to move from a lower energy level to a higher one, and is emitted when an electrons from a higher energy level to a lower one. This means that an electrons on the first energy level, in order to move to the second energy level, this must be absorbed by the second energy level. Or, in order for the third energy level to move to the second energy level, it must be emitted or released from that energy level to move to the lower. In the Bohr model, the lowest energy state available for an electron is the ground state, while all higher energy states are called the excited states. Okay, so let's talk about these orbitals and the quantum numbers. In the 1920s, Werner Heisenberg put forth his uncertainty principles, which states that at one time it is impossible to calculate both the momentum and the allocation of electron in an atom. It is only possible to calculate the probability of finding an electron within a given space. This meant that electrons, instead of traveling in a defined orbits or hard spherical shells as Bohr proposed, it travels in a diffuse clouds around the nucleus. Okay, so what are these quantum numbers? Quantum numbers are basically used to describe certain aspects of location of the electrons. For example, the quantum numbers n, l, m1 describes the position of electron with respect to the nucleus, the shape of orbitals and its special orientation, while the quantum number ms describes the directions of the electron spin within a given orbital. Okay, so to clarify, quantum numbers n describes the position of the electron with respect to a nucleus. Quantum numbers L describes the shapes of the orbitals, and M1 describes the special orientation. Okay, so principal shell or the quantum numbers n. First is we have energy level 1 or as shell K. Second energy level 2 with the name L. Energy level 3 or the M shell, and the last fourth energy level or the N shell. For quantum numbers, principal quantum number or the small n or italicized n. This designates the principal electron shell or the energy level. Because n describes the most probable distance of the electrons from the nucleus, the larger the number of n, the farther the electron is from the nucleus. The larger the size of the orbital and the larger the atom is. N can be any positive integer starting at 1, as n is equals to 1 designates the first principal shell or the innermost. When n is equals to 2, therefore it is on the second principal shell. If n is 3, then it is on the third principal shell. First principal shell is also called the ground state or the lowest energy state. This explains why n cannot be 0 or any negative integer, because there exists no atoms with 0 or negative amount of energy levels or principal shells. When an electron is in an excited state or it gains energy, it may jump to the second principal shell where n is equals to 2. This is called the absorption because the electron is absorbing photons or energy. Known as emissions, electrons can also emit energy or release energy as they jump to lower principal shells, where n decreases by whole numbers. As the energy of the electron increases, so does the principal quantum number. For example, n equals to 3 indicates the third principal shell. N equals to 4 indicates the fourth principal shell, and so on. Example, n is equal to 1 or 2 or 3 or 4. Okay, for example, if n is equals to 7, what is the principal electron shell? Since n is equals to 7, therefore it is on the 7th principal shell. Okay, next example. If an electron jump from energy level n equal to 5 to energy level 3, did absorption or emission of a photon occur? The answer is emission, because energy is lost by release of a photon. From 5, it becomes 3. Release of energy. Next quantum number is the orbital angular momentum quantum number, or stands for small italicized L. This determines the shape of an orbital and the angular distribution. The number of angular nodes is equal to the value of the angular momentum quantum number L. Each value of L indicates a specific SPDF subshells which is unique in shapes. Okay, so let's look at the shape of each orbitals. First is the s orbitals, where L is equals to 0. S orbitals are spherically shaped regions describing where an electron can be found within a certain degree of probability. The shape of the orbital depends on the quantum numbers associated with the energy state. All s orbitals have L equals to m equals to 0, but the value of n can vary. Next is the p orbitals. It has L equals to 0 and 1. P orbitals are dumbbell-shaped or lobe region describing where an electron can be found with a certain degree of probability. The node of the dumbbell occurs at the atomic nucleus, so the probability of finding an electron in the nucleus is very low, but not zero. The shape of the orbital depends on the quantum numbers associated with the energy state. Next is d orbitals, where L can be 0, 1, and 2. D orbitals are clover-shaped because the electron is pushed out 4 times during the rotations when an opposite spin protons aligns gluons with 3 spin-aligned protons. And last is the F orbitals, where L can be 0, 1, 2, and 3. F orbitals are more complex but follows the same rules based on the proton alignments as the p and d orbitals. When completely full, it is similar to the d orbital but cut in half, or 8 lobes instead of 4. It is based on the points in the nucleus rotations where the gluons of the opposite spins protons align. Example 3. If n is equals to 7, what are the possible values of L? Answer: since L can be 0, or positive integer less than n minus 1, it can have a value of 0, 1, 2, 3, 4, 5, or 6. Example 4. If L is equals to 4, how many angular nodes does the atom have? The number of angular nodes is equal to the value of L, so the number of nodes is also 4. Okay, so the third quantum number, or the magnetic quantum number, or the M1. Magnetic quantum numbers determines the number of orbitals and their orientations within a subshell. Its value depends on the orbital angular momentum quantum number, L. Given a certain L, magnetic quantum number is an interval ranging from -1 to +1. So it can be 0, a negative integer, or a positive integer. Example: if n is equals to 3 and L is equals to 2, then what are the possible values of ML? Answer: since ML must range from -1 to +1, then ML can be -2, -1, 0, 1, or 2. Okay, so the last quantum number, the electron spin quantum number, or the MS. it does not depend on another quantum number. It designates the directions of the electron spin and may have a spin of positive 1/2 represented by arrow up or negative 1/2 represented by arrow down. Since that when ms is positive, the electron has an upward spin, which can be referred to as spin up. When it is negative, the electron has a downward spin, so it is a spin down. Its significance of the electron spin quantum number is its determination of an atom's ability to generate a magnetic field or not. ms equals to positive or negative 1/2. Okay, example 6. List the possible combination of all four quantum numbers when n is equals to 2, l is equals to 1, and ml is equals to 0. Answer: the fourth quantum number is independent on the first three, allowing the first three quantum numbers of two electrons to be the same. Since the spin can be positive or negative 1/2, since the spin can be positive 1/2 or 1/2, there are two combinations. N is equals to 2, L is equals to 1, ML is equals to 0, MS equals to positive 1/2, and N is equals to 2, L is equals to 1, ML equals to 0, MS is equals to negative 1/2. Okay. Example 7. Can an electron with ms 1/2 have a downward spin? Answer: no. If the value of ms is positive, the electron is spin up. Electron configurations. Electron configuration describes how electrons are distributed in its atomic orbitals. Electron configuration of atoms follow a standard notation in which all electron-containing atomic subshells, with the number of electrons they hold written in superscript, are placed in a sequence. For example, the electron configuration of sodium is 1s2, 2s2, 2p6, 3s1. Okay, so in this part, you have an electron configuration of hydrogen. For 1 is the energy level, S is the type of orbitals, and the exponent of 1 is the number of electrons in that orbital. Writing the electron configuration. The maximum number of electrons can be accommodated in a shell is based on the principal number n. It is represented by the formula 2 and 2, where n is the shell number, the shell's values of n, and the total number of electrons that can be accommodated are tabulated below. So these are the shell and the n value. K shell equals to 1, L shell 2, M shell 3, and N shell 4. The maximum electrons in the electron configuration is, for K shell we have 2, L shell we have 8, M shell 18, and N shell we have 32. The subshells into which electrons are distributed are based on the angular momentum quantum number, denoted by L. Principal quantum number value of 1. The L value is 0, and the resulting subshell in the electron configuration would be 1s. If the principal quantum number is 2, L value would be 0 and 1, resulting into 2s and 2p. If n is to 3, L value would be 0 or 1 or 2. Resulting subshell is 3s, 3p, 3d. If n value is 4, the L value is equals to 0, 1, 2, and 3. The resulting subshell would be 4s, 4p, 4d, and 4f. Okay, so how do we fill up these atomic orbitals? We are going to use the three principles. First, the Aufbau principle. Next is the Pauli exclusion principle and the Hans rule. Aufbau principle. This principle is named after the German word Aufbauen, which means build up. The Aufbau principle dictates that electrons will occupy the orbitals, having lower energies before occupying the higher energy orbitals. An energy of an orbital is calculated by the sum of the principal and the azimuthal quantum numbers. According to this principle, electrons are filled in the following order: 1s, 2s, 2p, 3s, 3p, 4s, 4d, 3d, 4p, 5s, 4d, 5p, 6s, 4f, 5d, 6p, 7s, 5f, 6d, 7p. Okay, so this is the figure of the Aufbau principle. So this n and the numbers indicates the principal numbers, while this is the angular momentum numbers or the L quantum numbers. This is equals to 0, the s orbitals, p orbitals, t orbitals, and f orbitals. Next is the Pauli exclusion principle. The Pauli exclusion principle states that a maximum of 2 electrons each having opposite spins can fit in an orbital. This principle can also be stated as no 2 electrons in the same atom have the same values for all quantum numbers. Therefore, if the principal, azimuthal, or the angular momentum quantum numbers and the magnetic numbers are the same for 2 electrons, they must have opposite spins. And the last is the Hans rule. This rule describes the order in which electrons are filled in all orbitals belonging to a subshell. It states that every orbital in a given subshell are singly occupied by electrons before a second electron is filled in an orbital. In order to maximize the total spin, the electrons in the orbitals that only contain 1 electrons all have the same spin or the same values of the spin or quantum number. So in this figure, the correct is this one, 1s2, 2s2, and 2p2, while this one is incorrect. Okay, so since your activity is all about writing a Hans rule, let's have this example. First, this is the complete orbital filling diagrams of the Hans rule. Okay, so this is your table would be look like with the elements of the third period, chemical symbol, sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, and argon. Then atomic number and the orbitals: 1s, 2s, 2p, 3s, and the 3p. So let's have the argon as for example. According to Pauli's exclusion principle, each orbital must have a 2 maximum electrons with 2 opposite spins. Okay, so for 1s, spin up, then spin down. So that would complete the first orbital. Second orbital be spin up, then spin down. That's another 2. For the p orbital, we have 3. We have 3 columns. What you're going to do is, if the first 2 orbitals does not meet the number of atomic number here, you're going to put first arrow, the spin up arrow. Spin up, another spin up, then spin up. Then you are going to put spin down on this part. Another spin up, spin up. Okay, so that would complete the orbital for 2p. So if you're going to count the number of electrons, is 2, 4, 6, 8, 10. And the number of atomic for argon is 18, so you need at least 8. Then for the next, you are going to put another spin up for 3s, then spin down for 3s also. Then for the 3p's, you have 3 column of 3p, put spin up 1, 2, 3, then spin down. So if you count that, you have 2, 4, 6, 8, 10, 12, 14, 16, 18. It would be equal to the atomic number of argon, which is 18. So this is the hand rules for chemical argon following the Pauli's exclusion principle.